Good morning. Today we're going to look at the basic elements that make up systems to be able to understand each one of the elements and understand its equations and how they role are on building complete systems that are used to build computer models. So let's begin now, and it's called Basic Modeling Concepts and Single Elements and Multi-Port Devices. So the first thing we're going to see is that we have in the world we have systems and the system variables. As you can see on the left hand side over here, we have a mechanical system here. Let me see, there it is. Right here we have a mechanical system here with a force and a velocity. Here the definition of power on the system is the force times the velocity is the power in a mechanical system. On the right hand side here we have an electrical system where you have the voltage and the current as the main power variables. Now here you have on the lower left a rotational system where you rotate a mass and a shaft in there, and the variables for power are the torque and the angular velocity. On this side, in a hydraulic system, we have the variables are the pressure and the volume flow rate. So we are at the crucial step, you may say, on the first homework on chapter 1. You are being asked to understand what these variables are. Now these are what we call power variables, because the variables that integrate or compose power in different energy domains are these ones: force, velocity for mechanical system, voltage, current for electrical system, torque and angular velocity for a rotational system, and pressure and volume flow rate for a hydraulic system. What I was trying to tell you the other day is that the thinking of Professor Painter, who discovered the technology of modeling mechatronic systems, he says we could call the first element the effort and the second one the flow, and have only that type of variables that will actually represent things in many energy domains. So if that's true, the word effort becomes force, voltage, torque, or pressure. The word flow becomes velocity, current, angular velocity, and volume flow rate. Conclusion: power is always the effort times the flow. Okay, so what we're doing basically is reducing the notation to the effort variables and the flow variables. So E and F equals P for power. Now the relationship between these variables E and the variable F to another set of two additional variables, which we're going to call it P and Q, goes through the derivation of those variables. So if you have the flow, like in this case on a mechanical system, the flow is going to be the velocity. It means the velocity is the derivative of the position. So dq dt is equal F. Or you can say that the force is equal to the rate of change of momentum, right? That we learn in E110 very much in several of chapters of that textbook. But the idea is that if you derive F, F is the derivative of dq dt, and E is the derivative of dp dt. And then it's this nice little pictures, just so you're to remember the variables. We call it Painter's tetrahedron of state, meaning these are the state variables. See, this P's and Q's always are the state variables. Now in chapter 1 in the textbook, when you were reading, you realized that oh, you know, he's asking me for state variables. Here we're going to make it a little easier, because once we put together systems, we know that P's and Q's, with all the denominations that we've seen a moment ago, are in fact the state variables. You want to make a little table in there to understand this a little better. What Painter is saying is easier that we operate with 4 variables than with 16. And he's right about that. I mean, he says, if I learn to operate with E and F and P and Q, it's better than operate with all these 16 variables that we have on the right hand side for systems in many energy domains, whether they are mechanical, electrical, or hydraulic systems, because that's what mechatronic systems are about. There's a combination of things. So in here, when we have this, we concentrate on E and F and P and Q, and we'll forget about learning all these things. Just the concept is what is important. Okay, so let's go take a look in here. In here, a little more detailed explanation. That in here you see there's a simple model of a battery in here, and the cables that go to the started of motor of a vehicle right here. And then when you turn your key, then the motor begins working, goes to the Bendix, and your car starts. How in the world do we make a simple model of that system? So you see, here's the battery, this is the motor, and this is the Bendix. And of course these are applications, perfect applications for cars. That's why it was very helpful for the Opel company when I was there to be able to see that here in the US we make models of systems used in vehicles very easily. So the Daimler-Benz in Germany is one of the ones that uses this technology actually in research and development and in production of their vehicles. I don't know if I told you, but the stabilizer system on a Mercedes-Benz, the one that actually corrects the position of the car if you take the curve too fast, that's a hydromechanical system that has sensors on what you're doing, and then has a control system that actually corrects the course, and that was designed with this technology. Anyway, notice one thing. Here's the voltage and the current as the variables of communication, the variables of communication between two sections of the system are in fact those power variables. Between the battery and the motor would be the voltage and the current, and between the motor and the Bendix would be the torque and the angular velocity. Okay, so let's go on with this now. If you have an entire car now, not just that system of the started, you see you have in here the engine, and it has the throttle, of course, that controls the engine, but that sends the power on the drive shaft with the torque and an angular velocity. In the middle of the gearbox and the engine there is the clutch. So the clutch in here has a control system because it is a switch basically. It's either connected with the engine or disconnected. So we modeled here this as a switch. Again, the power variables are again torque and angular velocity. The gearbox is a very interesting device because the gearbox, what it's doing is transforming one velocity into another. Go first gear, second, third gear. but the gear selection is a control system in the gearbox. So far we are only up to the gearbox, and you see there, to be able to make the car shift, we have 3 control systems. 1, the throttle; 2, whether the clutch engages or not; and 3, in which gear we have. And then you have the drive shaft, which is what makes the car go. That drive shaft goes to the differential gearbox, which is a box that is between the 2 axles, and then that goes to the wheel on the right, the wheel on the left. So, conclusion of this discussion: during the system of the modeling the entire vehicle, we have these torques, and then we have these angular velocities as the power variables that go between each one of the elements that we have. Okay? So let's go a little bit more in detailing here. This is a representation of the symbols that we use to make computer simulations. Either we use these block diagrams in here, or we use these bone graph models. So the information that we see on the block over here is the same that we see on the bone graph over here. Let's take a look at the first one here. You see in here it says A. See this arrow here? A presses on B with the variable E. B responds with the variable F. See, the arrow goes from A to B, and B goes from B to A. That could be between the battery and the motor, or between the gearbox and the shaft. It doesn't matter. It's just 2 elements on the system. But the same representation is made when you have this green line in here and this vertical bar. It says the same A that is over here presses on B, and we do this by representing with the vertical bar. But the response of B will go with this green line. So, because the concept is important, you could say, what is the output of A? The output of A is obviously the effort, because that effort is delivered from A to B. The output of B is going to be this flow, and that's delivered from B to A. So the same thing as A goes from A to B here with variable E, B goes from B to A with variable F. If you switch things around and you look at the picture on the right hand side, you know that in this case the variable that A imposes on B is F, and B responds with E. If we do that, then the representation of the bone graph model switches around, and that's what you see on the right hand side. So you see, you go from B to A with this effort, the red line, and then A responds towards B with the green line, which is the flow. So this is a very important basic principle that we need to use on everything. So I think that's why I make an emphasis to make one entire slide about this. In order to do computer simulations, we need 9 elements that we need. We need 2 sources, we need 2 connection elements, and we need 1 element that stores the kinetic energy, which we call it inertia element or I element. You see in there, we use inertia I element. Then we have a capacitive element or compliance element. We use the C element. Well, let's go with examples. I element is just a mass, or if it is in rotation, it would be rotational inertia. But the capacitive element is like spring, stores potential energy, and in this case we call it C element. And it's like a spring, as I said, or a capacitor on an electrical system. You have a resistive element, which is the one that dissipates energy, such as a shock absorber, for example, on a suspension of a car. In this case, we call it the R element. And then we have two conservative elements that do transformations. So let me summarize this. 9 elements, 2 sources, 2 connection elements, 1 element for the kinetic energy, second element for the potential energy, third element to dissipate energy, and then 2 elements that make transformations. Like a set of gears is a transformer, because it does not produce any power, but rather transforms one velocity into another, or one torque into another torque. So in here we have let's see, let's go on with this, and we are going to look at this concept of power and the little causal mark that we just learned a moment ago. We are going to use the way power flows from one element onto another with this little half arrow in here. See, if power goes from A to B, you put the half arrow like this. If power goes from B to A, you put it this way. Then you complete the whole thing. In this case, A imposes the effort on B, B responds with the flow, but power goes from A to B. That's what this means. In here, A imposes the flow on B, B responds with the effort, and then power goes from A to B. That's what this other picture means. Okay. In here there are 2 kinds of connections that we use. Different kind of connections. Remember, there's 2 elements, 2 connections. We use this 1 junction for this kind of connection, and we use the 0 junction for this kind. So depending on how you connect things, either you use a 1 or a 0. But the ones are 0 are elements that allow us to build the structure of a system, nothing else. So in here you see you have the mass, and the common variable here is the velocity, because you put the 1 junction in here and then you connect the F, which is the source here. You also have the I element, which is the mass. You connect the spring, which is the C element, and then you connect the damper, which is this R element. Now in here you see you have on this connection here, the common variable instead of the velocity is the force, because this one transmits to this and this transmits to that. Okay, so that's why we use the 0. But again, the effort here is this F, the mass is this I, the C is the spring, and then the R element is the damper. Okay, we're going to go and look at each one of the resistive elements in here, and then we'll go the R element, the C element, and the other ones, just so that we don't lose. So well, let's just put a little break in the